Okay, so we're going to look at a couple examples here, kind of a contextual interpretation for derivative. And before we do that, notice, so we have kind of a different notation here. So dr over dt. So r is our function, amount of rainfall, t is time, t hours after a thunderstorm begins. So this is just an alternative notation for a derivative. We've been using the prime notation, f prime, for example. This is just an alternative notation. So this is the derivative of r with respect to t. So we always have measuring the rate of change of one variable versus another variable. So in this case, we're measuring the rate of change of r as t changes. So you'll see that time from time to time. They'll be kind of used interchangeably as we go along. But what does this derivative mean in this context? So again, R is the amount of rainfall, T is time. So how is the amount of rainfall changing as an hour passes? So the notation dr over dt is a derivative of R with respect to T. So T is changing unit to unit. How much is R changing in that time, or the instantaneous rate of change? So the derivative is the instantaneous rate of change. So this is the rate at which rain is falling in inches per hour. So again, probably said this maybe in an earlier video, but slope and rates of change are always the y units per x units, or in this case, r units per t units. And then if it starts raining harder, you could say the dr dt is increasing at that moment. All right, so let's look at the next example. So here we have g of x representing the amount in gallons of gasoline remaining in a tank after being driven x miles. So interpret this expression. So again, dg. Now, and I said this right here. I noticed. You don't say dg over dx. You say dg dx. Or dy dx if we're just using x and y. Not a big deal, but just kind of that's typically how you say this. So this notation is dg dx, or the rate of change of gasoline with respect to miles, evaluated at x equals 50. We'll see this notation later again. But this just means you're evaluating this expression when x equals 50. So this is the rate at which the amount of gas remaining in the tank is changing when the car has been driven 50 miles. Okay, so these are pretty simple. Once you kind of get used to them, just remember slope is always change in y over change in x. So how is the y changing at this particular x value, or at whatever it is, whatever value x is. All right, so next, so now we're going to talk about second derivatives. So if f is a differentiable function, then its derivative f prime is also a function. We said that earlier. So f prime may have a derivative of its own. And we've kind of seen that. Maybe we could have guessed that. So we had a polynomial, we had a quadratic function earlier, and we took the derivative. The derivative was a linear function. We find the derivative of a linear function because we did that as well. So when you take the derivative of a derivative, we call that the second derivative, and it's denoted with two primes there since it's a second derivative, and we call it we call this f double prime. And so we'll see what that tells us. That does tell us things about the original function. It doesn't just tell us, obviously the second derivative would give us the rate of change of the first derivative, but it'll also tell us things about the original function as well. But all you do the derivative process twice to get the second derivative. It's not super complicated. Now is this the same 2x squared? And not exactly. All right, so we'll work this out just for the practice. So let's find the first derivative. So the limit as h goes to 0, f of x plus h minus f of x over h, and the limit as h goes to 0, and then we'll plug in the x plus h for each of the x's. So we have x plus h squared minus 8 x plus h minus 9, and then subtract the original function. All of that is over h. Let's FOIL out the x plus h squared. X squared plus 2xh plus 8 squared minus 8x minus 8h minus 9, and then we'll distribute the negative. So minus x squared plus 8x minus 9, and actually that should be a plus 9 right there, plus 9 there. And so how did I notice that? I don't have the function memorized, or I wouldn't have written minus 9 there, but how did I notice? Like I said in the last one that we did, all of the non-h terms should cancel out. So the x squared would cancel out, 8x would cancel out, and the 9s will cancel out. So when I noticed there's a minus 9 and a minus 9, so they should not be. They should cancel out. All right, so let's we'll go ahead and factor out the h. So we'll have h, and then just pull an h out from each of the terms that are left. And we should have that. The h's cancel. And now we can just plug in 0 for h, and the derivative is 2x minus 8. So that is our first derivative. Now we want to find the second derivative. So the derivative of a quadratic will always be a linear function. And the derivative of a linear function is always going to be a constant. And so, like we said a couple of times, the derivative is just slope. So if we have a linear function, we have a constant slope. Slope in this case is 2. So the derivative of this is 2. So the second derivative of the original function would be 2. All right. So what do derivatives tell us about a function? And we kind of already saw this when we did the very first example where we had the graph of the function and we wanted to sketch a graph of the derivative. We kind of use this idea, but we didn't explicitly say it. But whenever the derivative is positive, the function will be increasing on the interval. Whenever the derivative is negative, that's essentially saying the slope is negative. If the slope is negative, then the function is decreasing. So if it's known that the graph of f prime is shown, so this is the graph of the derivative, what can we say about the function? So what we can say here is the derivative is positive from, we'll just say negative infinity to -1. So f prime of x is greater than 0 on, and we'll say negative infinity to -1, and then also from 1 to infinity. And so that means it's increasing on that interval. And then f prime is less than 0 between -1 and 1. So that means it's decreasing on that interval. So now we can use that to sketch the graph, a possible graph, and of the function. And they give us that f of 0 is 0. And the reason I do that is because the vertical part of this doesn't matter. Like, you can't tell vertically where the graph is based on the derivative. All you can tell is it's increasing on these two intervals and it's decreasing on that interval. So we'll start here. We know it's, let's put -1 and put 1. We know that it's increasing till we get to here. So let's draw it like that. It's going to be decreasing from there to there, and then it's going to be increasing after that. Now, it doesn't necessarily, so just to give you an example, we could draw another one. It's increasing like this, so we could have something like this. This would still work. Put 1 there, put -1 there, goes through the origin. That would also work as a possible graph. So that the reason it says possible graph is because there are many ways that we could have a function increasing on these intervals and decreasing on that interval. There's nothing super special about this particular graph or this one. We could have multiple graphs, and it could come way up here. It could come down really fast. We don't know. But that's really all you can tell from the derivative is just the increasing and decreasing. You can't really tell particular values, and that's why they have to give you this, just to kind of give you some anchor, I guess. But don't get too hung up about, how did I know that we start down here? How did I know that we go up like that? I don't. It's a possible graph. There are many ways you could draw it. All we know is we're increasing to there, we are decreasing from there to there, and then we are increasing after that. All right. All right, so what does the second derivative tell us? If the second derivative is positive, then f is concave up. And so concave up looks like that. So it just means that you can think of it like a right side up bowl. If the second derivative is negative, it's concave down. That would be like an upside down bowl. So that's what we get from the second derivative. The second derivative is looking at the rate of change of the function slope. So is the function slope increasing or is it decreasing? So let's look at this graph. So we have the graph shows the population for honeybees over what interval is P concave up or down. And usually, so it's concave up here. So concave up to there. At some point, we can tell this part is concave down. At some point, it changes. And just you can kind of make your best guess. It's usually about halfway between, but we'll say there. So it's concave up from 0 to 12, and then concave down from 12 to 18 in this case. And then this is actually called, so that last little note there, it's called an inflection point. And so an inflection point is just wherever it changes from concave up to concave down or vice versa. So there's a lot in this section. And I would suggest make sure you understand the terms and the parts. What does the derivative tell us? What does the second derivative tell us? The more you kind of get used to these things, think them through. Don't just try to memorize that answer, for instance. Try to be able to do this on your own as much as you can without having to look things up. Of course, when you first start, you got to look things up, but do it enough to where you can pretty instinctively do this. Like I said, on the first example, the graphs were the hardest part for me. I mean, some people have to struggle with other things, but I know this can be a little bit tricky at first. So just the more you practice, the easier it will get.